Merhaba arkadaşlar. Beni duyabiliyor musunuz? Sesle ya da görüntüde bir problem var mı?
Sesim sıkıntı yok hocam.
Şu an duyabiliyor musunuz?
Sesle görüntüde bir sıkıntı yok hocam. Duyabiliyoruz.
Duyuyorsunuz değil mi?
Evet hocam, sesle görüntü de gayet iyi.
Tamam, teşekkür ediyorum. Ben emin olamadım. Bana ses problemli geliyordu. Başlıyorum o zaman. Umarım iyisinizdir. Geçtiğimiz hafta artık sonunda CPU scheduling'den bahsetmeye başladık. Çeşitli algoritmalardan bahsettik. Bu algoritmaları nasıl uygulayabileceğimizden bahsettik. Ama bu bölümü tamamlayamamıştık. Küçük bir kısmımız daha var. Geçen haftaki kadar uzun olmasa da CPU scheduling hakkında konuşmamız gereken birkaç şey daha var. Çünkü geçen hafta konuştuğumuz kısım özellikle şeyi varsayıyorduk. Evet, prosesler var. Bunları belirli bir sırayla çalıştırmamız gerekiyor. Bu sırayı belirleyebilmek için de çeşitli algoritmalar kullanabiliriz ama oradaki varsayımımız bizim bir single core CPU üzerinde bu işlemleri yaptığımız üzerineydi. Dolayısıyla algoritmaların nasıl çalıştığını kavramak açısından iyi bir yöntem ama gerçekte aslında artık ne yapıyoruz? Daha fazla işlemci kullanıyoruz. Yani fiziksel olarak daha fazla çip kullanmasak da hani bir dönem öyleydi. Birden fazla çip üzerinde birden fazla işlemci popülerdi başlangıçta. Ama sonra ne oldu? Tek bir çip üzerinde birden fazla core kullanmaya başladık. Hatta artık ne yapıyoruz? Bir de sanal çekirdeklerimiz var. Yani birazdan onlardan da bahsedeceğiz. Örneğin benim şu an kullandığım bilgisayarda öyle. Aslında fiziksel olarak 4 tane çekirdek var bunun içerisinde ama bir de hardware seviyesinde scheduling yapılıyor. İşlemci oradaki core'ları 8 taneymiş gibi varsayıyor. Yani biz işlemci tarafından baktığımız için 8 core varmış gibi işlemlerimizi yapmaya devam edebiliyoruz. Ama aslında fiziksel olarak orada 4 tane core var. Her neyse sonuç olarak şey kısmına da değinmemiz lazım. Evet, elimizde algoritmalar var, scheduling yapabiliyoruz ama bu işlemleri yaparken, bu işlemleri multiprocessor side'da yaparken nelerle karşılaşabiliriz? Temel yaklaşımlar nelerdir? En azından bunlardan bir bahsetmemiz lazım. Ardından da birden fazla scheduling algoritmasından bahsettik. Bunları nasıl kıyaslarız, nasıl karşılaştırırız, seçim nasıl yaparız bunlar arasında? Kısaca onlardan bahsederiz. Bu haftayı aslında böylece bitirmiş oluruz. Ardından muhtemelen vaktimiz kalacaktır. Bu geçtiğimiz hafta bahsettiğimiz algoritmaların örneklerini çözeriz. En azından birer tane. First come first served, short job first, işte round robin, priority bunları nasıl uygulayabiliriz? Bunların birer örneğini çözeriz. Önümüzdeki hafta vizelerden önceki son hafta olacak. O yüzden yeni bir konuya geçmek istemiyorum önümüzdeki hafta. Önümüzdeki hafta şöyle yaparız. Kısa bir tekrar yapabiliriz şu ana kadar üzerinde konuştuğumuz kısımlar hakkında. Bir de bunun dışında sorularınız varsa bu sorularınızı bana e-mail ile gönderebilirsiniz. Önümüzdeki hafta bu sorularınızı cevaplamaya çalışırım. Yani ders saatini aslında bir tekrar ve soru cevap şeklinde ilerletebiliriz. Var mı sorusu olan, söylemek istediği bir şey olan yoksa başlayalım.
Hocam,
Efendim,
kitaptan nereleri çözelim tam olarak? Yani
kitaptan mı anlamadım.
soru olarak hani
Çalışmak için mi, hazırlık için mi?
evet hocam. Evet.
Yani egzersizleri aslında kitabın chapter'ların sonundaki egzersizleri çözebilirsiniz. Yani konuları kavramada da yardımcı olacaktır. Ama işte zaten geçtiğimiz haftaya kadarki olan kısım hayli teorikti. Tabii ki genel konseptlerden bahsettik ama e, özellikle geçtiğimiz hafta daha algoritmik, daha uygulamaya yönelik, daha gerçekçi problemlerin çözülebileceği kısımlar vardı. Dolayısıyla bu CPU scheduling'e kadar genel konseptler hakkında bilgi sahibi olmak, oradaki genel egzersizleri, genel soruları gözden geçirmek yeterli olur ama CPU scheduling kısmında işte belirli set prosesler üzerinde bu algoritmaların nasıl uygulanacağına dair alıştırmalar yapmak, çözümler yapmak iyi gelir. Bugün zaten birkaç örneğinden bahsedeceğim.
Sağ olun hocam.
Var mı başka soru? Başlıyorum. Okay then, last week we started to discuss CPU scheduling on operating systems, and we discussed some specific algorithms based on that manner. This week we are going to focus on the multiprocessor scheduling and the selection of scheduling algorithms. So let's start with multiprocessor scheduling. As I said already, our discussion thus far has focused on the problems of scheduling the CPU in a system with a single processing core. If multiple CPUs are available, load sharing where multiple threads may run in parallel becomes possible. So scheduling issues become more complex based on that manner. Many possibilities have been tried, and as we saw with CPU scheduling with a single core CPU, there's no one best solution based on the station. The best solution can be different. Traditionally, the term multiprocessor referred to systems that provide multiple physical processors, where each processor contained one single core CPU. However, the definition of multiprocessor has evolved, has changed significantly. And on our modern computing systems, multiprocessor now applies to these architectures, these systems. We have multi-core CPUs, we have multi-threaded cores, we have NUMA systems and heterogeneous multiprocessing. So we're going to focus on these architectures. The standard approach for supporting multiprocessor is called as symmetric multiprocessing, or SMP, where each processor is self-scheduling. Scheduling proceeds by having the scheduler for each processor, which examine the ready queue and select a thread to run. So note that this provides two possible strategies for organizing the threads to be scheduled. The first one, all threads may be in a common ready queue, and the second one, each processor may have its own private queue of threads. These two strategies has presented on this figure. If we select the first option is on the left side, common ready queue. All threads may be in a common ready queue. If we select that option, we have a possible race condition on the shared ready queue, and therefore we must ensure that two separate processors do not choose to schedule the same thread, and that threads are not lost from the queue. On the other hand, the second option permits each processor to schedule threads from its private run queue, and therefore does not suffer from the possible performance problems associated with a shared run queue. So it's the most common approach on systems supporting symmetric multiprocessing. So if we have a symmetric multiprocessor, actually, if we want to use symmetric multiprocessing, it's a common way to use per core run queues. In a traditional way, symmetric multiprocessing systems have allowed several processes to run in parallel by providing multiple physical processors. However, most contemporary computer hardware now places multiple computing cores on the same physical chip, resulting in a multi-core processor. Each core maintains its architectural state and thus appears to the operating systems to be a separate logical CPU. SMP systems that use multi-core processors are faster than and consume less power than systems in which each CPU has its own physical chip. Multi-core processors may complicate scheduling issues. So let's consider how this can happen. We know that actually the researchers have discovered that when a processor accesses memory, it spends a significant amount of time waiting for the data to become available. This station, known as a memory stall, it occurs primarily because modern processors operate at, let's say, much faster speeds than memory. Our processors operate faster than our memory. So for that reason, we can faced with a problem that can be called as memory stall. However, a memory stall can also occur because of cache miss. So this figure illustrates a memory stall. In this scenario, the processor can spend up to 50% of its time waiting for data to become available for memory. So at the beginning, we have let's say we have a thread, we have a process, and we start to execute that process on CPU. But at some point, we need to get data from memory. So we have to wait for the data to become accessible. And on that time, the CPU could be idle. So that means we have a compute cycle, then we have to wait for data, then we have another compute cycle, then we have to wait for data. So that waiting can be spanned up to 50% of the time of execution. To solve this problem, to create a solution to this situation, our recent hardware designs have implemented multi-threaded processing core in which 2 or more hardware threads are assigned to each one. So in that case, okay, we have more than one threads assigned to each core. So that way, if one hardware thread stalls while waiting for memory, the core can switch to another thread. So this figure illustrates a dual threaded processing core on which the execution of thread 0 and the execution of thread 1 are interleaved. Basically, we have 2 threads, while the first thread, let's say thread 0 on the memory stall, we can execute the thread 1. Also, when the thread 1 on the memory stall, we can execute the thread 2. So basically, we have just single core on this station, but hardware assumes that actually works like we have 2 different cores. From the operating system's perspective, each hardware thread maintains its architectural state, such as instruction pointer and register set, and thus appears as a logical CPU that's available to run a software thread. This technique, known as chip multithreading, which is illustrated in this figure. Here, the processor contains 4 computing cores, with each core containing 2 hardware threads. From the perspective of the operating system, on a quad-core system with 2 hardware threads per core, the operating system sees 8 logical processors. Okay, the hardware thread can be provided by the processor on the hardware level, but if we have two hardware threads on each core, and if we have a quad core processor, the operating system is going to view that processor as we have 8 different CPUs. So on the operating system side, we have to manage our scheduling mechanism based on the operating system's view. Also, it's important to understand that the resources of the physical core, such as caches and pipelines, must be shared among its hardware threads, and therefore a processing core can only execute one hardware thread at a time. So consequently, a multi-threaded, multi-core processor actually requires two different levels of scheduling, as shown in this figure, which illustrates a dual-threaded processing core. On one level are the scheduling decisions that must be made by the operating system as it chooses which software thread to run on each hardware thread. So actually, we have a logical CPU on that. We have to decide which thread we're going to run on which core. For all practical purposes, such decisions have been the primary focus of this chapter. Actually, we are focusing on how we can schedule the threads on CPUs. So on the logical way, okay, we have a processing core with two hardware threads. On the operating system side, so on the logical way, we are assuming that, okay, we have two different CPUs and we are going to make the scheduling, we are going to select the scheduling method based on that. Therefore, for this level of scheduling, the operating system may choose any scheduling algorithm, including those we described last week. A second level of scheduling specifies how each core decides which hardware thread to run. There are several strategies to adopt in this station. One approach is to use a simple round-robin algorithm to schedule a hardware thread to the processing core. So that would be the basic way to execute two different hardware threads. But again, actually, we are focusing on the first level on this chapter. On SMP systems, it's important to keep the workload balanced among all processors to fully utilize the benefits of having more than one processor. Otherwise, one or more processors may sit idle while other processors have high workloads, along with ready queues of threads awaiting the CPU. Load balancing attempts to keep the workload evenly distributed across all processors in an SMP system. It's important to note that load balancing is typically necessary only on systems where each processor has its own private ready queue of threads to execute. On systems with a common ready queue, load balancing is unnecessary because once a processor becomes idle, it immediately extracts a runnable thread from the common ready queue. All processors use the common ready queue. So you don't need to create a load balancing mechanism on that station. There are two general approaches to load balancing. They're called as push migration and pull migration. With push migration, a specific task periodically checks the load on each processor, and if it finds an imbalance, evenly distributed the load by moving or pushing threads from overloaded processors to idle processor or less busy processors. Pull migration occurs when an idle processor pulls a waiting task from a busy processor. So push and pull migration need not be mutually exclusive and are in fact they often implemented in parallel on load balancing systems. So consider what happens to cache memory when a thread has been running on a specific processor. the data most recently accessed by the thread populate the cache for the processor. As a result, successive memory access by the thread are often satisfied in cache memory. Actually, it's called as warm cache. So now consider what happens if the thread migrates another processor, say due to load balancing. One process is executing on a processor, so it creates a warm cache. It accesses their data based on that processor, and assume that we are migrating that process from one processor to another processor to create a load balancing mechanism. The contents of cache memory must be invalidated for the first processor, and the cache for the second processor must be repopulated. That process needs to access the same data. The contents of cache memory must be invalidated, as I said, for the first processor, and on the second processor, on the new processor, we have to repopulate that data. Because of the high cost of invalidating and repopulating cache, most operating systems with SMP supports try to avoid migrating a thread from one processor to another, and instead attempt to keep a thread running on the same processor and take advantage of the warm cache. So this part is important. Okay, if we have more than one processor, we want to work that processors, we want to utilize that processors, but for that manner we have to create a load balancing mechanism. To load balancing, we can use push migration or pull migration, but both of them means we have to move one process from a busy processor to an idle processor. But if we move the process, we can face up with different issues. Every process has its own data access, and every process has its own cache on the processor. If we move the process, we also invalidate the cache on the first processor and repopulate the cache on the second processor. So this is a costly operation. For that reason, okay, we need some load balancing mechanisms, but most systems try not to migrate processors. So basically, the basic reason of that is using the warm cache, taking the advantage of the warm cache. So actually, this is known as processor affinity. That is, a process has an affinity for the processor on which it's currently running. Processor affinity takes several forms. When an operating system has a policy of attempting to keep a process running on the same processor, but not guaranteeing that it will do so, we have a situation known as soft affinity. Okay, we have an affinity, but the system does not guarantee that that process will always run on the same processor. So here, the operating system will attempt to keep a process on a single processor, but it's possible for a process to migrate between processors during load balancing. In contrast, some systems provide system calls that support, let's say, hard affinity. In that case, allowing a process to specify a subset of processors on which it can run. Many systems provide both soft and hard affinity. You can use based on your needs. The main memory architecture of a system can affect processors' affinity issues as well. So this figure illustrates an architecture featuring non-uniform memory access, or NUMA, non-uniform memory access, where there are two physical processor chips, each with their own CPU and local memory. Although a system interconnects allows all CPUs in a non-uniform memory access system to share one physical address space. A CPU has faster access to its local memory than to memory local to another CPU. If the operating system's central processing unit scheduler and memory placement algorithms are non-uniform memory access aware and work together, then a thread that has been scheduled onto a particular CPU can be allocated memory closest to where the CPU resides, thus providing the thread the fastest possible memory access. Okay, let's continue with real-time CPU scheduling. CPU scheduling for real-time operating systems involves some special issues. In general, we can distinguish between soft real-time systems and hard real-time systems. Soft real-time systems provide no guarantee as to when a critical real-time process will be scheduled. They guarantee only that process will be given preference over non-critical processes. On the other hand, hard real-time systems have stricter requirements. A task must be serviced by its deadline. Service after the deadline has expired is the same as no service at all. In this section, we explore several issues related to process scheduling in both soft and hard real-time operating systems. Actually, I'm going to pass them. Okay, we have some operating system examples on our book based on Linux scheduling, Windows scheduling, and Solaris scheduling. I'm not going to get the details about that, but I recommend you to take a look at Linux scheduling and Windows scheduling. So here's the question. We know we have different scheduling algorithms to select a process to execute on CPU. So this is the question. How do we select a CPU scheduling algorithm for a particular system? So as we saw last week, there are many scheduling algorithms, each with its own parameters. As a result, selecting an algorithm can be difficult. The first problem is defining the criteria to be used in selecting an algorithm. As we saw in last week's course, criteria are often defined in terms of CPU utilization, response time, or throughput. To select an algorithm, we must first define the relative importance of these elements. Once the selection criteria have been defined, we want to evaluate the algorithms under consideration. One major class of evaluation method is analytical evaluation. Analytical evaluation uses the given algorithm and then system workload to produce a formula or number to evaluate the performance of the algorithm for that workload. Deterministic modeling is one type of analytic evaluation. This method takes a particular predetermined workload and defines the performance of each algorithm for that workload. For example, assume that we have the workload shown as that figure. We have 5 processes. All 5 processes arrive at time 0 in the order given as P1, P2, P3, P4, and P5, with the length of the CPU burst given in milliseconds 10, 29, 3, 7, and 12 milliseconds. So this is our workload. So based on that workload, we can make using deterministic modeling, we can make an analytical evaluation. So here is the solution. Consider the first come, first served, shortest job first, and round robin with a quantum of 10 milliseconds. Scheduling algorithms, we are going to compare that algorithms. We have first come, first served, shortest job first, and round robin with 10 milliseconds of quantum. So which algorithm would give the minimum average waiting time can be considered as the question we are going to look for an answer. For the first come first served algorithm, we would execute the processes as shown in that Gantt chart. The waiting time will be 0 milliseconds for process 1, 10 milliseconds for process 2, 39 milliseconds for process 3, 42 milliseconds for process 4, and 49 milliseconds for process 5. So based on that, the average waiting time with this set of processes for first come first served algorithm will be 28 milliseconds. If we use a non-preemptive short job first scheduling, we can execute that processes like that. The waiting time will be 10 milliseconds for process 1, 32 milliseconds for process 2, 0 milliseconds for process 3, 3 milliseconds for process 4, and 20 milliseconds for process 5. So based on that, the average waiting time for this set of processes using the non-preemptive short job first algorithm will be 13 milliseconds. With the round robin, with time quantum 10 milliseconds, the execution of processes will be like in this Gantt chart. So here we have 0 milliseconds waiting time for P1, 32 milliseconds for process 2, 20 milliseconds for process 3, 23 milliseconds for process 4, and 40 milliseconds for process 5. So based on that, the average waiting time for this set of processes using round robin will be 23 milliseconds. So we can see that in this case, the average waiting time obtained with the short job first algorithm is less than half that obtained with the first come first served scheduling. And the round robin algorithm gives us an intermediate value between the first come first served algorithm and short job first algorithm. So deterministic modeling is simple and fast. It gives us exact numbers, allowing us to compare the algorithms. Okay, we have a set of processes, we know the algorithms, and we can analyze them. We can compare with the exact numbers. However, it requires exact numbers for input, and its answers apply only to those cases. These characteristics only valid for this set of processes. So the main uses of deterministic modeling are in describing scheduling algorithms and providing examples. So this is the best way to understand how this algorithm works. Based on this deterministic analyzing, we can describe how this algorithm works, and we can provide some examples, but it will not be easy to implement that in a real system because we don't have the exact numbers of inputs. On many systems, the process that are run can be different from day to day. So there is no static set of processes or times to use for deterministic modeling. So what can be determined, however, is the distribution of CPU and I/O bursts. These distributions can be measured and then approximated or simply estimated. The result is a mathematical formula describing the probability of a particular CPU burst. Commonly, this distribution is exponential and is described by its mean. Similarly, we can describe the distribution of times when processes arrive in this system. From these two distributions, it's possible to compute the average throughput, utilization, waiting time, and so on for most algorithms. The computer system is described as a network of servers, each server has a queue of waiting processes. The CPU is a server with its ready queue, as is the I/O system with its device queues. Knowing arrival rates and service rates, we can compute utilization, average queue length, average waiting time, and so on. So this area of study is called as queuing network analysis. As an example, let N be the average long-term queue length, so excluding the process being services. Let W be the average waiting time in the queue, and let lambda be the average arrival rate for new processes in the queue. So we are going to describe the Liddell's formula using that information. So we expect that during the time W that a process waits, lambda times W new processes will arrive in the queue. Okay, we already have a queue and we have a process on that queue, and the average waiting time that for that process on that queue is W, and based on the average arrival rate, because we know that new processes will arrive that queue, based on that we can assume that lambda times W new processes will arrive at the same queue with that time. If the system is in a steady state, then the number of processes leaving the queue must be equal to number of processes that arrive, because actually it's a ratio, it's a rate. So based on that, the number of new coming processes must be equal to number of leaving processes. So based on that, N will be equal to lambda times W. This equation is known as Liddell's formula, which is particularly useful because it's valid for any scheduling algorithm and arrival distribution. We can use Liddell's formula to compute one of the three variables if we know other two. If you know lambda and W, you can get N. If you know N and lambda, you can get W. For example, if you know that 7 processes arrive every second, actually it will be average, and that there are normally 14 processes in the queue, then we can compute the average waiting time per process as 2 seconds. So based on that, we can say that the average waiting time for processes on that ready queue will be 2 seconds. Actually, queuing models are often only approximation of real systems, and the accuracy of the computed results may be questionable. To get a more accurate evaluation of scheduling algorithms, we can use simulations. Running simulations involves programming a model of computer system. Software data structures represent the major components of the system. The simulator has a variable representing a clock. As this variable value is increased, the simulator modifies the system state to reflect the activities of the devices, the processes, and the scheduler. As the simulation executes, statistics that indicate algorithm performance are gathered and printed. The data to derive the simulation can be generated in several different ways. The most common method uses a random number generator that is programmed to generate processes, CPU burst times, arrivals, departures, and so on, according to the probability distribution. The distributions can be defined mathematically or it can be defined empirically. If a distribution is to be defined empirically, measurement of the actual system under study are taken. The results define the distribution of events in the real system. This distribution can then be used to derive the simulation. However, a distribution-driven simulation may be inaccurate again because of relationship between successive events in the real system. The frequency of distribution indicates only how many instances of each event occur. It does not indicate anything about the order of their occurrence. To correct this problem, we can use trace files. We create a trace by monitoring the real system and recording the sequence of actual events. We then use this sequence to drive the simulation. So we can observe the system, and based on that, we can get the real values which worked on that system. So trace files provide an excellent way to compare two algorithms on exactly same set of real inputs. This method can produce more accurate results for its inputs. Even, as you know, even a simulation is of limited accuracy. The only completely accurate way to evaluate a scheduling algorithm is to code it up, put it in the operating system, and see how it works. This approach, of course, puts the actual algorithm in the real system for evaluation under real operating systems. And that's it for this chapter. So we considered actually the special issues with the multiprocessor system, multi-core systems, and then we focused on how we can choose the correct algorithm, how we can compare the scheduling algorithms based on different methods. And that's it for this chapter. Any question? Var mı soru?
Hocam bu affinity kısmını Türkçe özet geçebilir misiniz?
Tabii. Şimdi birden fazla prosesörün varsa ne yapmak istersin? Sen bir load balancing yapmak istersin. Değil mi? Yani 8 tane CPU'm var. Bunlardan sadece 5 tanesi çalışıyor, 3 tanesi boşsa, bütün işte threadlerim 5'i için schedule edildi, 3 tanesi boş çalışıyorsa bu verimli bir durum değil. Yani 8 core'un varsa, 8 CPU'un varsa bunların hepsini verimli olarak kullanmak istersin. Dolayısıyla bir load balancing mekanizmasına ihtiyaç duyuyoruz burada. Load balancing nasıl yapılabiliyor aslında? En temel yolu migration. Yani burada çalışan bir prosesi, atıyorum iki prosesör olduğunu düşünelim kolaylık olması için. Birincide çalışan bir prosesi alıyorsun ikinci prosese. Niye? İkinci boş çünkü. Birinci çok yoğun çalışıyor. Birden ikiye alıyorsun. Buna migration deniyor. İki yöntem olabilir. Push ve pull. Orayı geçiyorum. Böylece load balancing'i yapabilirsin. Ne oldu böylece? P1 yani birinci core'unda, birinci prosesöründe çalışan bir prosesi ikinciye almış oldun. Böylece ikinci de boş durmuyor artık. Ama burada şöyle bir problem çıkıyor. Zaten cache kullanımını biliyoruz ya. Cache kullanımı nedir? Bir proses veriye ihtiyaç duydukça aslında o veri yakınlaşır. Ne kadar çok aynı veriye ihtiyaç duyuyorsa o aslında o kadar yakınlaşır. Yani artık diskte değildir, işte memory'de değildir, cache'dedir. Buna işte warm cache deniyor. Bu proses 1'in çok ihtiyaç duyduğu veriler, sık kullandığı veriler warm cache'de. Çok kolay erişebiliyor. Ama ben bu prosesi ilk prosesörden ikinci prosesöre taşıdığım zaman ne oluyor? Öncelikle o ilk taraftaki cache'i invalidate etmem lazım. O artık kullanılabilir değil. Çünkü cache'ler aslında proseslere özel. Dolayısıyla orayı invalidate etmem lazım. Bu ikinci prosesörde de aynı işte warm cache'i yaratmam lazım. Verileri tekrar oraya doğru çekmem lazım. Bu bir süreç. Maliyetli bir süreç. O yüzden evet load balancing mühimdir. Migration'la load balancing yapılabilir ama çok tercih edilen bir yöntem değil. Niye? Çünkü sen bir CPU boşta kalmasın diye aslında daha yüksek bir maliyet çıkarmış oluyorsun kendine. Olabilirsin diyelim çoğu durumda. Bu yüzden Affinity kullanılır. Affinity aslında işte P1 prosesör 1'de çalışıyorsa ona affine olsun. Orada çalışmaya devam etsin. P2'ye taşınmasın demek. Bunun için soft affinity var, hard affinity var. Soft affinity'de genellikle böyle oluyor. Diyor ki tamam P1'i define ettiğim prosesörde çalıştırırım ama hani çok önemli bir durum olursa migrate edebilirim. Sana garanti vermiyor. Buna çalışacağım ama böyle de olabilir. Bu soft definity. Hard definity'de de polisi sana şeyin garantisini veriyor. Evet bu P1 prosesör 1'de çalışacak. Bunun garantisini veriyor. Aslında definity bu. Bir prosesle bir prosesörü define etmiş oluyorsun. O orada çalışacak anlamına gelmiş oluyor. Ve aslında bu her iki yöntemde kullanılabilir. Genelde işletim sistemleri bu her iki yöntemi de destekler. İşte şeyin özellikleriyle, prosesin özellikleriyle sen derken işletim sistemin buna karar verebilir. Oldu mu?
Sağ olun hocam.
Başka soru? O zaman bir ara verelim. 15 dakika. 10.30'da buradayım. Şu biraz önceki şeyde olduğu gibi, şu örnekte olduğu gibi aslında deterministik olarak bir set üzerinde algoritmalarımızı nasıl karşılaştırırız? Bunun üzerine birkaç tane örnek çözelim. Görüşmek üzere.